lines and planes. The one issue with this lesson is that there's too much to do. It's impossible for me to hit every single question type, so I'm going to ask you to use a little bit of your ingenuity and a little bit of your skill to try to solve out some of these things that are not exactly what we think. I shouldn't say that. To solve out the types of questions that I don't show here. But the types of things I'll do will give you a good baseline to work from. Again, let's update our understanding of parametric definitions of lines. So like, let's say I have this point out here. I call it 1, 2, 3, 1, 2, 3, 4, 5. I have this coordinate 3, 5. And then I throw some slope through it. Let's go 1, 2, 3, and 2. Right, so that's where I'm rising and running. Excellent. But it's not, I'm not going to be using y equals mx plus b, because the thing that is changing it is that it's parametric. This line is now dependent on t. So if I'm turning this thing into a vector, the idea is that my vector is going to start by pointing here, leaving some wide space, 3, 5, and then my vector will be changing over time. As t changes, my vector will continue to go from the origin following that change. So that change comes from my slope. That 2 over 3, my y's are changing 2 per every x changing 3, and it doesn't matter how infinitesimally small I get, I've now defined this forever and ever. I can go into the negatives and start counting backwards. I could stay in the positives and keep counting forwards. This is my parametric definition of the line. I could even go as far to say, hey, x of t is 3 plus 3t. Y of t is 5 plus 2t. Independent, codependent, two space. So now it asks me to find an equation through this parallel to this. So when it says parallel, right, it's trying to get me or you to think of slope. And the slope that's going to change the same is this 1, 4, negative 2. So I'll really just put it together. Typically, this is how we'll write the equation of a line. The vector function t, that's going to output in 3 vector components. The first one starts at 5, and it varies by 1t. The next one starts at 1 and varies by 4t. The next one starts at 3 and varies by negative 2t. Right, and I can pop this out into ijk format. 5 plus t parentheses I plus 1 plus 4t j, 3 minus 2t k. Right, all kind of within our stuff. Where it says find any other point on the line, my variable is t. So I'm just going to choose a new t value to find a new point. So if I plug in t is 1, it's just plug, plug, plug. 5 plus 1 is 6. 1 plus 4 is 5. 3 minus 2 is 1. That's not a point. This is a point. I don't know why I made it a vector. But that's another point on the line. And again, if I wanted to find a point and a slope, I could take a derivative and find a slope. But we're going to save that. We're going to save that for Unit 13, because Unit 13 entirely focuses on the study of this type of interaction. Next, we have a special type of equation, a format called symmetric equations, where it says, hey, if t is involved in all of these, what if I solve them all for t? That's to say, if x equals 5 plus t, y equals 1 plus 4t, and z equals 3 minus 2t, what if I solve them all for t? T equals x minus 5, t equals y minus 1 divided by 4, t equals z minus 3 over negative 2. I believe in you to do that algebra. Well, since they're all equal to t, they're all equal to each other. And this is called the symmetric form of our equation. The nice thing is, what I take from that symmetric form, if I pop a denominator in here, what I take from that symmetric form is this is my point that I started with, and this is my slope. So if you get symmetric form, you know that your slope, your m, your direction, comes from here, the amount of t in each of these, whereas the point comes from my standard, x minus h, y minus k, z minus l situation. Write the equation for the line through here and here. So I'm going to get a point and I'm going to get a slope and put them together. That's all I'm doing. I might make a vector that talks about how I change from A to B. Right? If I label this point A and I label this point B, the vector from A to B will tell me the slope or change from one to the next. Well, I could take a point, I could take a slope, and it'll work. And I could take this point and this slope and still put them together to make that parametrically defined function of a line. Let's put that together real quick. In this case, I would go x is 1 plus 2t, y is 3 minus 1t, and z is 2 plus 3t. Last but not least, again, I could solve those all into that symmetric format. X minus 1 over 2, y minus 3 over negative 1, z minus 2 over 3. Really nice, really interchangeable, etc. So when it asks me to figure out if they intersect, this is where it gets interesting, because I cannot say that these are equal to t. Generally, we would make a new parameter. We would call it s. And so if I'm building this thing out into that s format, I'd have x is 3 plus s, y is 1 plus 2s, and z is 5 plus s. And I want to see when my x's and y's are equal. So the best way to test this is to kind of make two systems of equations and see if they coexist. Let me show you. If x is equal to x, meaning they coexist in the same place on x, then 1 plus 2t ought to equal 3 plus s. Well, if they're going to be coexisting on y, then 3 minus t ought to equal 1 plus 2s. And I would work to solve this system of equations. Now over here I might multiply, or over down here I might multiply by 2. And I would get 6 minus 2t is 2 plus 4s. Now I would kind of combine my x and new y equations. Stick with me. 7 equals 5 plus 5s, where s equals 2 over 5. Well then, if s equals 2 over 5, I can work back and solve for t. Combine these, subtract. So, I've only been using x and y, and I know that when s is 2/5 and t is 6/5, x and y are the same. So I have the same kind of x and y, but are they sitting at the same height on z? Well, all I have to do is plug them in and verify I get the same z value out. So when I do z is 2 plus 3 times 6/5, and down here z equals 5 plus 2/5, are they going to be equal? I get 28/5 up here. Down here I get 27/5. Oh, a near miss. But that's the truth. They are not going to intersect. They're going to be just barely separated in space. And again, I check that by saying, well, I set the x's and y's, I force them to coexist, I force them to be equal. Do I occupy the same z space? Other things you could do is you could simply test something that, like, hey, when x equals 1, am I going to get the same out? But that starts to get into some weird stuff. A much more foolproof way is to just try to set these equal, make a system, and depend on the third variable. I usually save t to verify they're in the same height as they are occupying the same x, y. So when I left off, we said that when I dot things together, we had this idea of the triple product. And let's see if I have enough space to talk about it up here. We said if C dot A cross B made 0, that means that they coexisted in the same plane. Because A cross B made a parallelogram, and C was a vector going in a supposedly different direction. But if they're all laying flat on the same plane, A cross B will extend 0 in the direction of C. Remember that dot product is saying how far does C go into the same direction as A cross B, or how far does A cross B go into the same direction as C? These things, when I dot them together, would be coplanar. Again, remembering, this gives me the volume of the parallelepiped, and if that volume is 0, that means it's flattened, and that means these things are coplanar. It also means if I'm dot producting two things together and getting 0, well, that means that it's perpendicular, because a dot product is a cosine relationship, and if the cosine is 0, that means these things are perpendicular. So we are going to use this fact to build the equation of a plane, where in general a plane is just going to be some x plus some y plus some z and a constant. And you might think that we'd like to start with things are parallel, but if we know this, let's just build from the fact that these are going to be perpendicular and they're going to make a 0, which is really easy to solve against, the same reason we factor against a 0. So, right, C is perpendicular to A and B if C is perpendicular to A cross B if C dot A cross B is 0. I'm kind of saying the same thing a bunch of times. Sorry, I had to pause and check myself because it started coming out funny and I wanted to make sure I got it right. So we are going to use this perpendicularness, this good perpendicularness, to build something. And so what you're likely going to see, right, is I'm going to have some plane that I'm building. Oops, that was a bad start. Right, staying parallel here, staying parallel here, and building out this nice plane. But it relies on the fact that I have some normal direction sticking directly out of it. And so I'm going to call this normal vector n. And all I need is the point. If I have a point and a normal vector, I have enough to make the equation of a plane. And I'll just rely on this fact. Watch this happen. I'm just going to say my point is some generic x naught, y naught, z naught. My n is my normal vector. It's perpendicular to the surface. Well, that means to make that plane, 0 is equal to n dot. Well, wait a second. This needs to be a vector. If I'm going to dot these things together, this needs to be a vector. Well, just choose any generic x, any generic y, and any generic z, and you will be making vectors from this point to those places in space with that normal forced to be equal to 0. So you're going to find all of the things that have to occupy that perpendicular space. You're, by default, just generically selecting all of the points that fill that perpendicular space. And so I can know that two planes are parallel if and only if they share a common vector. A common normal, sorry. So, if I find two planes that have a common normal, I know that they are parallel. And now we have a bunch of examples, and again, I cannot cover every example type, but I'm going to do my best to do so. Find a plane through this point with this normal. This is a very basic, generic plane equation, right? I'm going to take this normal, 2, 3, 4, and I'm going to dot it with x minus 2, my generic x minus 2, right? Just shift it in space. Y minus 4, just shift it in space. Z plus 1, just shift it in space. And when I dot these together, 2 times x minus 2 plus 3 times y minus 4 plus 4 times z plus 1. All of a sudden, it's starting to take that same shape that I defined at the start that we lost a little bit in the middle because of our definition and guaranteeing that we're finding the equation that represents all points that lie perpendicular, coplanar with that. It makes the volume of 0. Now we're just doing some algebra here, folks. 2x minus 4 plus 3y minus 12 plus 4z plus 4. Combining my like terms and moving them to the other side. 2x plus 3y plus 4z minus 12. And I get my final equation. 2x plus 3y plus 4z is 12. And I can pull the normal right off this, right? At the end of the day, if I get the equation of the plane, notice my normal is just right there. 2, 3, 4. Legible. And we can use that heavily in the future. How about this? Find the equation of a plane through these 3 points. How do I find, right, if I have 3 points in space, I'll just call them P, Q, and R. They're all sitting on this beautiful sheet of paper. Dang, this pen's drying out. How do I find something that's going to make a right angle and shoot out here, straight out of that sheet of paper? I know that right angle was pretty poor. Right angle there, right angle there. But that's the concept. What forces right angles to exist? A cross product. Now you see it's all one song, folks. I'll do a vector PQ, and I'll get 2, negative 4, 4. I'll blaze through that. I'll do vector QR. I guess my picture's a little bit false then, but you still see the same idea. Yep, because we know that these are going to be coplanar points, I'm still allowed, I could do PQ, QR, PQ, QP, RP, like all of these options are available to me. 2, 3, negative 6. One thing I will do in situations like this, because I know this holds the same direction as this guy, I'm going to shrink it down just to save myself a little bit. Divide all my components by 2. It's still headed in the same direction, so I can still make something that's perpendicular without worrying about changing my direction just by scaling my numbers down a little bit. And I know that this cross product is going to do what I want it to. I, J, K, 1, negative 2, 2, 2, 3, negative 6. And let's go. 12 minus 6i minus negative 6 minus 4. J, that's a lot of negatives. 3 plus 4k. And so I'd get that vector here. And this thing is guaranteed to be orthogonal to these. So now I have my normal vector, now I have a point, and I just put them together. Right? I poorly managed my space here, so hold on. It worked when I practiced, and all of a sudden I lost track of where I was. So now I'll take a normal and a point, which is all it takes to make a plane. So my plane is going to be 0 equals my normal, 6, 10, 7, dotted with a vector. Now I could choose one of these vectors and it would totally work out fine. I want to do this. Let's choose the easy one, 520, y minus 2, z minus 0, and just dot these things together. The 0 is just going to save me a little bit of work, not too much though. 6 times x minus 5 10y minus 2 and 7z. Again, when I combine these all, they work out. Trust me here, 10y plus 7z makes 50. And again, I can read my normal directly off of this. My normal 6, 10, 7, always good to keep in mind. And then it's almost like I have a 3D shift of 50 units where I'm adding 50 to the total, or I'm forcing this constraint, these multiplications to be constrained to 50, which gives me this versus all of the others. Because if it said, hey, find another plane parallel to this one, 6x plus 10y plus 7z equals 25, right? They have the same slope, but a different beginning point. All right. On to the last one, a tricky that, yes, two planes intersect, and this intersection will be what shape? Right? If I have two planes intersecting, it's like a repeated lines intersecting forever, and it generates a line. So you need to be careful. Again, this word is suggesting these things are equal. Well, if I know these things are equal, I'll be able to kind of set some things equal to each other. Not only that, I know that I'm breaking down the question saying an angle between. This is asking me to do a dot or a cross product. I'm much more likely to do a dot product because it's a little bit quicker and easier. Well, if it wants me to make these two things equal, they kind of already are. This is equal to 1, that's equal to 1. I'll just set them equal to each other. X plus y plus z equals x minus 2y plus 3z. But it doesn't work out so perfectly. Right, my x's cancel, and I'm just left with this relationship. And when I combine my y's, I'd get what? 3y equals 2z, y equals 2/3 z. And what you see here is this is a line, right? It's absent of x. X doesn't matter, but it makes a line. All right, and that line looks like this. R of t. Well, this is my rise and run. This is my change. For every 3y, I move 2z. Well, I just need a coordinate that works. Now this part is a little bit trickier, choosing a coordinate that works, finding a combination of x, y, and z that work. But thankfully, I know that x is kind of independent on this problem. So if I set x equal to 1 and y equal to 0 and z equal to 0, that satisfies this plane. If I set 1, 0, 0, that satisfies that plane. So that'll be my point. And now I'll make a change vector. X does not matter. 2 or 3 y's for every 2 z's. This is a third way we have to write lines. Not only in that x is this plus this t, y is this plus that t, z is that plus that t. We can also list them as a combination of vectors because it results in a vector. Last but not least, well, I can take the two normals, and the way those normals cross ensure that I get the angle of intersection between them. Again, A, I'll call this guy B. I should probably call it normal 1 and normal 2. A has a magnitude of 1, 1, 1, that's rad 3. B has a magnitude of 1, 2, 3, that's 14. And now I just use my A dot B over the magnitudes is cosine of that angle of intersection. I dot them together and I get A dot B is 1 minus 2 plus 3. Yep, which makes 2. And so 2 over rad 3 times rad 14 is cosine. I use that inverse cosine function, and I get my final angle of intersection between the two planes to be 7202. As you can tell, these dot/cross products have far-reaching implications. This video went way too long, I hope it was helpful. Have a lovely day.